Yes, and with that said, we come to our next speaker, Tetsuya, who works for a Japanese company called Kozo Keikaku Engineering. They are active OAI users. I think it's not the first time that you're at the workshop, right? And yes, he will present now the OAI-based wireless digital twin with SDR channel emulator. Welcome.
Thank you. So, hello, I'm Tetsuya from Kozo Keikaku Engineering in Japan, and thank you very much for this opportunity, and it is truly honored to be here. Today, I will present our SDL-based channel emulator and the OAI-based wireless digital twin we built with it. So let me start with the motivation. Toward 6G, full-stack validation is becoming essential for AI-native networks and more complex use cases. So, however, real-world OTA experiments have three major pain points: high cost and time-consuming radio licensing, and limited reproducibility. So this creates a serious reality gap. And our goal is to bridge this gap between realistic experiments and flexible simulation. To bridge this gap, the platform choice is important. This table compares major 5G open source platforms, and OAI covers the broadest scope, including 5G-C, RAN, UE, OTA experiments with SDRs or ORUs, and ORAN. On the other hand, NVIDIA, Aerial, and Siona provide GPU-accelerated system link level and ray tracing simulation. So combining these platforms for full-stack validation is a quite natural approach. So now I will explain our methodology. We start from a cable-connected OAI setup. A USRP-based G-Node B is directly connected to a commercial QuickTel UE. So we can test 5G signals without radiating RF. If we replace the cable with antennas, this becomes a full OTA setup. But then we need a radio license and or a controlled facility such as an echoic chamber, shielded tent, or shielded box. And this greatly increases both cost and setup effort. So instead, we take a different approach. We pre-compute the dynamic radio propagation scenarios using ray tracing in advance. And this gives us realistic time-varying channel data before running the actual experiment. And then we apply them directly to the cable transmitted signals by convolving the baseband signal with the channel impulse response, or CIR. So since this requires precise high-speed signal processing, we offload it to the FPGA on the USRP. By inserting this SDR-based channel emulator between G-Node B and UE, both downlink and uplink signals reflect the wireless environment. In this way, we can emulate field-like dynamic wireless environment without using radio wave. So next, let me explain how we compute the CIR. First, we build a 3D model of the environment. In this work, we used Plateau, Open High Fidelity 3D City Model project led by the Japanese government. OpenStreetMap is also a practical option. And for vehicle mobility, we use Sumo. By combining 3D CD data with mobility traces, we perform ray tracing at arbitrary time intervals and calculate CIRs. The key takeaway here is that all tools in this workflow are open source. And the raw CIR from ray tracing is a set of delayed complex paths as shown on the left. After sampling and bandwidth limiting filtering for a digital communication system, it becomes somewhat smoother as shown in the middle. And convolving the entire CIR is costly, so we sort the components by amplitude and keep only the dominant ones. These CIRs are applied to the baseband IQ stream through convolution. On the FPGA, this is implemented as a tapped delay line structure, TDL structure. And the signal is shifted by each delay and summed over the available taps. So using this test bed, we conduct scenario-based experiments. For FR1, the setup is the same as the one shown earlier. For FR2, the setup on UE side is different. The quick-through FR2 module does not expose signal lines, so cable-connected testing requires OAI UE and another USRP. So this is our actual office setup. The GPU server is used for ray tracing and is placed in a separate room. It's not shown in this picture. The channel emulator and G-Node B and UE are located here in the lab. During the experiment, the control PC for the channel emulator shows CIR as a real-time power delay profile. It can also show path gain and the scenario video when available. At the same time, communication KPIs are monitored through the OAI box dashboard. So these are the main specifications of our X410-based channel emulator. It supports up to 100 megahertz bandwidth, up to 24 taps, 3GPP TDL models, manual multipass configuration, and SISO or 2x2 MIMO. The minimum CIR update interval is 200 microseconds, which supports Doppler shifts up to about 1 kilohertz. So here is the Shibuya mobility scenario used in our evaluation. We emulate 1-to-1 5G communication in a dense urban scene with moving vehicles. The scenario includes a bus blockage event where the target UE temporarily loses line of sight. We update the CIR every 200 microseconds and applied it using 24-tap convolution. So here are the FR2 28 gigahertz ray tracing results. The G-Node B uses an 8x8 array beamforming and tracks the blue-colored target vehicle, assuming its position is known. The blockage causes a very large path gain drop, much more severe than in FR1. However, the selected delay taps still remain within the CP limit. Now let's look at the emulation results. The RSRP trend measured in OAI follows the path gain variation from Sionna quite well. However, when loss blockage causes a sharp RSRP drop, the UE is often temporarily detached from the G-Node B. These are the main findings from the FR2 emulation. The relative power variation looks reasonable. And inter-symbol interference is not a major issue in this scenario. Still, blockage remains a serious challenge. So this is another FR2 scenario where the G node B knows the angular of departure of the best path and always steers the beam in that direction. This is the ideal simulation-based case. So when the loss path is blocked, the beam is redirected toward the strongest n-loss path to recover the gain. The right figure shows the path gain variation. The orange curve is this scenario, and the blue curve is the previous one. We can see that this approach mitigates the blockage effect and reduces the gain drop by about 20 to 30 dB. This is scenario. And when the loss path exists, the beam directed toward the car. But once the blockage occurred, the beam redirects to the n-loss strongest path. Since we do not, I will not replay the looped scenario repeated here. But in this case, the UE no longer detached, and the scenario could run continuously over multiple loops. So by comparing these two scenarios, we can say that to mitigate this blockage issue, we need more robust beam management or coverage from multiple RUs. So finally, we consider Doppler effects in these scenarios. The vehicle speed reaches up to 40 kilometers per hour in this scenario. For FR2, the fading period is about 1 millisecond. Our CIR update interval is 200 microseconds, so it is fast enough to capture the channel dynamics. So a bit fast, but to summarize, we developed an SDR-based channel emulator and built an OAI-based wireless digital twin using OSS and open data. By combining high-fidelity ray tracing with real-time SDR emulation, we evaluated blockage effects in a dense urban scenario. As next steps, we will extend the platform to multiple G node B and multiple UE scenarios. Wider bandwidths up to 400 megahertz, and larger NTN scale delays, and calibration with using real measurement data. And that's all. Thank you for your listening.
There are two questions. We have enough time for both.
For the multi-UE support, what's the architecture? You need multiple USRPs to emulate one channel per user, or you can emulate multiple UEs in one?
Actually, we have already started to develop another FPGA board, using another FPGA board, which have multiple TX and RX ports to support multiple UE and multiple G node B scenario. We have started to develop. But multiple means at this point up to 3 or 4 or something. Okay. And if we use MIMO, the supported node number is decreased.
My question was regarding channel generation. You had a phase where you were reordering the tabs. Why was that needed?
Sorry.
So, so basically you get a channel, basically the paths, delays, and gains from Sena.
Mm-hmm.
You generate a channel, sample it, then you were doing reordering the tabs. If you go back slides.
Okay. You mean filtering? No. Sorry. This one.
Yeah, exactly. So after the filter, so there is step of reordering basically.
Yes.
For the gains.
Yeah, because if we try to convolute every tabs, maybe in this case up to 150 or 300 tabs, it's computationally heavy. So we just extract the main contribution from the channel impulse response by reordering, and the strongest twin. In this case, we used 24 tabs from the top.
Yeah,
that's why.
I missed the x-axis. You said sorted index.
Yeah.
So I thought you were alternating the delays.
Yeah.
That's what.
So sorry, a bit confused.
Okay, thank you.
Thank you.